development. And the second part is the major part. It's about the classification and the basic principles of various types of energy storage technologies. And the third part, if we have time, we will cover the key characteristics and the applications of these different kinds of energy storage technologies. Okay, let's begin. Okay, the intended learning outcomes include to how you to know about the different energy storage technologies and to understand the basic working principles of these energy storage technologies. Okay. This is a photo of the electrochemical energy storage station in the Tibetan Autonomous Prefecture in Qinghai Province. Just a photo. Okay, first of all, we have the background. Just recall to the first lecture, the primary energy demand has gradually decarbonized. In the 2024, the solar and the wind power account for about 15% of the total global energy mix. However, there are some obstacles when we develop a green energy mix, because there is a temporal mismatch between the renewables and the building load. We can see here, there are fluctuations and emittance for the solar energy and for the wind turbines. So if it requires to find a way to ensure a constant and reliable energy supply for our building load. You can see the load profiles here is quite different to the PV and the wind turbine power generation flow profiles. Okay. So we should find a way to produce the reliable energy for our built environment. Here is a point, that is the electricity transport, generation and transport and distribution. It is a simple one-way system. That means the electricity generated should be used precisely when produced. So how much electricity we produce, and we use it directly, instantly. Okay. So that's why if the PV panels and the wind turbines generate power, we cannot use it directly. It will be a wasted or the curtail for the wind power or for the solar power. So that's why we need the energy storage technology. It is crucial for developing a renewable energy dominating energy system, because it can allow the energy production and the load to be decoupled from each other. Okay, it can transform the temporal intermittent renewable energy, the unstable and renewable energy into a controllable energy that we want to use. We want to control for the built environment. So that's why we need the energy storage. We can see here, when the renewable energy generation exceeds the load, you can see the low curve is the red line. So there are some renewable energy generation exceeds the low profile. So this amount of the surplus energy have to be curtailed if we don't have any energy storage. So if we have the energy storage, you can store this part of energy for later use. Okay, so there are also some shortage of the load. You can see. the red line is above the green part. That means the renewable energy generation falls short of the load here. So if we have the storage, we can use the stored energy to satisfy this sufficient part. Okay. Also, there is other usage for the energy storage technology. For example, when we design electricity generation system, there may be some maximum demand that will only last for a few hours each year. That means the peak hours may only last for a few hours each year. So if we design and build a power generation based on the maximum demand, based on the peak demand, there will be a waste because it only operates for a few hours each year. So that we can use the energy storage for the peak shaving and the load leveling. Just for the peak hours, we can use the energy stored in the storage to satisfy the peak hour. Then we can reduce the capacity of the power generation plant and to reduce the cost. So that's another usage application scenarios for the energy storage technologies. Okay. So it also has an important role in the electric vehicles. So, for example, in China, there is a rapid growth in recent years for the development of the electric vehicles. You can see. And China's cumulative sales of the electric vehicles has ranked the first globally for the six consecutive years. Okay. This is also driven by the development of the lithium-ion energy storage technologies. From the government aspect, countries around the world also release some policies to drive the advancement of the energy storage. You can see in December 2020, the U.S. Department of Energy released an energy storage grant challenge scheme. They aim to accelerate the development, commercialization, and the utilization of the next generation energy storage technologies and sustain American global leadership in energy storage. Okay. There are some targets of the scheme. For example, some initial focal targets, which are important for the commercialization of such technologies. They would like to achieve relatively very low manufacturing cost of such storage technology to drive the industry development. Okay. In terms of Europe, they also released a scheme called Battery 2013 Plus to support the development of the battery. This scheme involves a set of the policy initiatives to support the goal of making Europe climate neutral in 2050. Okay. For example, the aims of this Battery 2013 Plus scheme include how to invent ultra-high performance batteries that are safe, affordable, sustainable, and a long lifetime. And they also want to develop their value chain for these high performance batteries. Okay. And in terms of China, for example, in July 2021, the Chinese government released the policy the guiding options on accelerating the development of new energy storage. The main goal is to achieve the 13 gigawatts of the new stationary energy storage by 2025. Okay, what does the new stationary energy storage mean? It refers to the advanced and electrical energy storage technology, excluding pumped hydro storage. Just like the energy storage technology, including the pumped hydro storage, just means include all of other energy storage technologies. Okay. So how is this effect of this scheme? As of the end of 2020, the China's total new energy storage was approximately 3.8 gigawatts. But 4 years later, it reaches more than 48 gigawatts. So it not only hit the goal, but also beyond the goal. Okay, so this marking the rapid and the remarkable growth of China's energy storage and the industry. Okay, you can see a year-on-year growth is more than 100%. So very quick, very rapid growth of the total industry. So here is the background for the energy storage technology, for the reason, for the motivation, and from the government's scheme, the actions. Okay, now we will have some technical issues, do some technical learning points here. Okay, the second part is about the classification and the basic principle of the energy storage technologies. And you are expected to know the basic classification and the basic principles. And you can tell the difference between different kinds of these technologies. Okay. So here is a graph that demonstrates the classification of energy storage. It's quite complicated when you first look at it. But we can look at it one by one, okay? We can classify the technologies based on the form of energy they store. If we store the electrical energy in a mechanical form, then we have the pump hydro, the compressed air, and the flywheel. These three transfer the electricity into a mechanical form, no matter the gravitational and the kinetic, we will cover later. And also, you can transfer the electrical energy into the thermal energy. Like we have you can store it in a sensible heat form or a latent heat form. Okay, and you can also transform the electrical energy into a chemical energy form. Like we have the battery, what is the most dominant technology in this field. Okay, and we also have the hydrogen and fuel cell, and we have the chemical reaction heat. Okay, and finally we have the direct conversion between electrical and the electrical. It contains the supercapacitor and the superconducting magnetic, these two kinds. And we will cover some of them today. Okay. This slide gives you an overview of how is the market like today. You can see by the end of 2020, in the world there is about 200 gigawatts for the total installed capacity of the energy storage. And the major contributor is the pump hydro. it accounts for about 19% of the total energy storage technologies. Okay. And the batteries only accounts for 7.5% by the end of 2020. And in China, it's almost the same. And we can see the number here. The installed capacity in China is about 35 gigawatts, which accounts for about 18% of the overall installed capacity in the world. Okay, 20% share, like. And in terms, by the end of the of 2023, the total installed capacity increased from the 200 gigawatts to about 219 gigawatts. And the share of the pump hydro declined from 19% to 16.7%. And the share of the battery increased from like 7.5% to about 13%. So there is a huge increase in terms of the share of the battery. Okay, and in China, the total installed capacity is 86 gigawatts, and the share of it also increased from about 20% to 30%. So China is a key contributor in terms of this industry and market. Okay. And also you can find by the end of 2020, the lithium-ion battery only maybe accounts for 90% of the total installed capacity of batteries. And by the end of 2023, the share increased to about 97%. So it means almost all the battery we use for energy storage today are lithium-ion battery. So it plays a very important role in the energy storage overall industry and market. Okay. This slide shows the maturity of different energy storage technologies, and we can see here the x-axis demonstrate the maturity level. Okay, from the research, development, demonstration, deployment, and mature. And the y-axis demonstrate the technical risk of the basic demand. Okay, and we can just focus on the x-axis. Okay, we can see the pump hydro placed to the right on this side. It is the most mature technology nowadays. And then we have the lithium ions, compressed air energy storage. This figure is drawn in 2020, and I think in nowadays the lithium-ion battery will move to the right. Yes, it's quite mature today. Okay. Now we will have the very first one is the pump hydro, which is most widely used today. But before that, I would like to introduce some characteristic parameters to you at the very first. This will give you, because we will discuss some of the characteristics for each technologies. So maybe I think it will be good for you to have an overview beforehand. Okay, so like the energy, power, energy density, and power density, and the response time, how fast this technology can respond to the requirement, and the charge and discharge time. Self-discharge, it means if you place the battery there will be a loss of the energy storage along the time. Okay, and this one is very important. So round trip efficiency. Okay, for electricity in, electricity out. So how much we can get out of from the initial energy. So round-trip efficiency is very important. Okay, also we have some indicators for the commercialization, like cycle lifetime, and capital cost. Okay, we will cover much like the energy, power, energy density, power density, and the round-trip efficiency. We will see these indicators many times. Okay. Okay, you can see this table give you the numbers of the levels of different kinds of the technologies. Okay. So I want to clarify the difference between energy and power, because we will talk about this many times. So there are two main types of the energy storage, like the high energy type and the high power type. So high energy type means the technology can provide energy for a long period, like beyond hours. And high power type means the system can deliver energy at a very high rate for short durations. You can see here the unit of the energy is used like joules, the energy unit, right? The watt hours, kilowatt hours. It means the capacity to do work. You can compare it like to the amount of the water stored in a tank. Okay, so a bottle of water, how much water there is. And in terms of the power, it relates with the concept of rate. So there will be a time, okay? The unit used like watts. And you can compare it like the speed at which the water flow out of the tank. Okay, so these are the difference, energy and power. Okay, let's begin the learning of the pumped hydro energy storage. So the pumped hydro is the most widely used and well-developed and large-scale energy storage technology in the world. And it consists of the upper and lower reservoirs. Okay, you can see here the upper reservoir and the lower reservoir. And it also has pumps and turbines, motors, and generators. Because pumps, you use pumps to pump water from the lower reservoir to the upper reservoir. Use the excess electricity. Then the excess electricity can be stored as the gravitational potential energy in the water, right? So when other power generation facilities are sufficient, the stored water is released to the low reservoir and driving the turbine to generate electricity. So this is the basic principle of the pump hydro. It transfers the electrical energy into a mechanical energy, which specifically is gravitational potential energy. Okay. So we can use the equation we're very familiar to calculate the energy stored. The pump hydro typically have a very large capacity, so very like greater than 100 megawatts, and the height difference range from 100 to 800 meters, and the efficiency is like the round-trip efficiency is like the 75 to 18%, and it has a long lifespan of like 30 to 15 years, and it can fast response. Okay, here is a little video, we can have a look.
A Australia has a big challenge ahead with its energy supply. Almost 3/4 of Australia's energy comes from coal, which will decrease in coming decades as coal stations close down. We'll need huge amounts of new energy generation to replace it, and renewables such as wind and solar are the cleanest and cheapest option. That's where Tasmania can help. We're looking at the potential to double Tasmania's electricity generating capacity by changing the way we use our existing hydropower system and by adding pumped hydro storage to help fill the gap when the wind isn't blowing or the sun isn't shining. Normal hydropower is created by storing water on high ground and running it downhill to spin a turbine at the bottom. Once the water's past one or more turbines, it flows on out to sea. Pumped hydro captures and stores water in two places with a steep drop in between. Water can be pumped uphill to reuse for power generation again and again. Of course, that pumping consumes electricity in itself. That's where wind and solar power come in. Pumped hydro, wind and solar complement each other beautifully, providing a stable, reliable, clean energy system. When the wind blows and the sun shines, but people aren't using much power, excess wind and solar power is available to pump water back up into storage. At other times, when the wind and sunlight aren't generating enough power to meet demand, the pumped hydropower system swings into action and makes up the shortfall. The whole system works together like a giant renewable battery, providing the storage, reliability and flexibility that wind and solar can't offer on their own. Tasmania has lots of steep hills that were perfect for building hydro over the past century and are ideal for developing pumped hydro today. All this new electricity and storage would...
Okay. As the video said, the pump hydro technology can integrate with the renewable energy because it has rapid response, like a time span of 20 seconds to a few minutes, so it's very quick. It has rotation inertia because there is turbine and generator, so it can provide the rotation inertia there. As we know, the PV panel generates direct current. Okay, so there is no rotational inertia from the PV panels. Okay, so there will be lack of the rotational inertia, and pump hydro can compensate this part. Another advantage is pump hydro has the black start capability. It means it can start on its own, and it do not need any other external energy supply to initiate the start of the system. Okay. So based on whether it is connected to a flowing water body, and it can be classified into the open loop. It's connected to a natural water body and a closed loop. Okay. If we don't have the natural water reservoir, and we can build some artificial reservoirs to build such pump hydro energy system. Okay. Here are some examples of the pump hydro system throughout the world. Oh, this part will skip. Okay. Let's see the development of the pump hydro system technology. The very first pump hydro storage project was built in the 1890 in Europe. Okay, and in the 1960s, because of the dominance of the nuclear energy technology, this slowed the development of the pump hydro energy storage technology. So it wasn't until the development of the renewable energies that the pump hydro renewal has attracted attention again. So it evolved into the most widely used mature and large-scale solution used today. Okay, you can see the share of the different countries. China currently ranked first, and followed by the US and Japan. And in terms of the development in China, China actually starts at relatively late compared to other developed countries, and it begins in the 1960s, and currently, of course, it ranked first in the world. And the majority of the pump hydro projects are placed in South China, Central China, North China, along the coast, you can see. Okay, and about 47% of these systems were built before 2010 to support peak shaving, rather than the integration with renewables. Okay. And here is an example, Guangzhou pump hydro storage power system. This is the China's first large-scale pump storage system, and its capacity is 2.4 million kilowatts. And the water difference, the high difference of the upper and the lower reservoirs is about 500 meters. Okay. This station was built to ensure the stable and safe operation of the Daya-1 nuclear power plant. It's used for like peak shaving, frequency regulation, phase modulation, and emergency backup for the Guangzhou power grid. It has been operated for 30 years and generated exceeding 17 billion kilowatts, and this amount is equivalent to the annual electricity consumption of the residents in the Greater Bay Area. So it has made an important contribution to the society development. Now next we will have the compressed air. Okay. So compressed air energy storage consists of the compressor. They connect in a serial. Compressor, the electrical motor or engine, and turbines, and the energy storage containers. So the basic working principle is that excessive electricity is used to drive the compressor to compress air to store in a cavern. And when the power generation is not sufficient, the compressed air is expanded through the turbine to drive the turbine to generate electricity. So it's like this way. Okay, you can see this long way. From the excessive electricity to drive the compressor to compress air, which convert the electrical energy into the molecular internal energy. This is also a form of mechanical energy. And then when the power is insufficient, the compressed air to expand and to drive the turbines to generate electricity again. Okay, and both the compression and the expansion process can be carried out in multiple stages. And the compressed air pressure typically between 15 and 18 bar, so it's very high temperature, high pressure. And there is heat management requirement, because when the compressor performs work on the air temperature will rise, right? Generate heat. We have to remove this part of heat. And when the air to drive the turbine to generate electricity, there will be there will be temperature decline. So we will have to compensate this part of the heat to the air. So there will be cooling and reheating requirement inside this technology. So in terms of the storage, the air is typically stored in some underground caverns, such as depleted salt mines. Okay. Also, this compressed air storage technology is suitable for the large-scale applications. So how to remove the heat and reheat the air? There are several ways. For example, we can use the intercooling to remove the heat and use the combustion to reheat the air. Okay, and we can also use a thermal storage here to store the heat in the process of the compression, and this part of the heat can be reused in the process of the expansion. So it involves a thermal storage tank. Okay, here is another video.
요리사는 어떻게 유명해질까? 별을 많이.
In the fray are Arda in developing Adele, an adiabatic compressed air reservoir for use in generating electricity. The following animation shows how this project works. Where does the electricity go when there isn't enough demand for it? Adele can store it. The system works just like a huge battery that temporarily stores the energy in the form of compressed air. It all begins with an electrically driven compressor. Normal ambient air is compressed to around 70 bar. This is about 35 times the pressure of a car tire. Heat is generated in the same way as an air pump, around 600 degrees Celsius with Adele. The innovation: this heat energy is not wasted, but rather put to use in an efficient manner. The hot air is forwarded to large heat accumulators that are pressure tight and well insulated, so they are able to store the precious energy for a long time without incurring appreciable losses. The compressed air inside the accumulator flows through a branched network of pipes through ceramic materials, thereby transferring its heat to them. Next, the compressed air that has cooled down considerably is passed on to an underground salt cavern, a huge natural cavity. Salt caverns have been used for decades as storage reservoirs for natural gas, for instance. This is where the compressed air is stored until it is needed again. When the demand for power changes and more electricity is needed, or the weather changes and calm conditions cause the wind turbines to stop turning, Adele can fill in reliably on short notice. The compressed air inside the caverns that has cooled down to around 40 degrees Celsius is released once again. The flow moves towards the turbine under high pressure. To ensure that it doesn't freeze, which would normally happen, it needs to be heated up inside the heat accumulator. From here, the air flows to the turbine and rotates its blades. The generator that produces the electricity is connected to the turbine. The electricity flows into the grid for a short time and thus contributes towards a reliable power supply. Adele is thus an ideal buffer and a flexible partner for expanding the use of renewable energy.
Okay, and we can see the development of this technology. In the 1940s, U.S. Get the very first patent of this technology, and in the late 1970s, we have the first demonstration project in the world. It was constructed in Germany. Okay, actually, U.S. proposed some demonstration project, but it canceled. So it goes through a very difficult time. And if the first demonstration project in USA is in the 1990s, and then we have several other projects in all over the world. Actually, the development of process of this technology has not been very smooth because there is lack of the suitable application scenario where this technology is indispensable. Because we can also use the hydro pump hydro, okay, to just use in the similar application scenarios. So it cannot find its indispensable application scenario. So that's why it developed not so smooth. Okay. So here is the example of the first demonstration project. It is the Humtorf plant built in Germany in late 1970s. And the storage capacity is about 3 million cubic meters consisting of 2 salt caverns. And carbon stator is still in operation, and with an annual runtime of about 200 hours per year. Here are some details about this example. The configuration of a system consists of 2-stage compression and 2-stage expansion. After it successfully operating for 28 years, and it got refurbished in 2006. And this refurbish increased the original power output from to beyond 300 megawatts, and efficiency is is lower compared to the pump hydro, right? It's only 0.4. Next, we will have the flywheel. Flywheel also transfer the energy into a mechanical way. Okay, a flywheel consists of a flywheel rotor. So this is the very the core component of a flywheel. Okay, and the motor and the generators and some bearings. Okay, this forms the flywheel system. And magnetic bearings are used to lower the mechanical wear and to lower the energy consumption. And the excessive electricity are stored in the form of kinetic energy. The electricity drives the motor to spin, and the flywheel will spin at a high speed. Okay, when there is insufficient power generation, the flywheel drives the generator to produce electricity. So just transform this electrical energy into the kinetic energy. So the energy stored in flywheel can be calculated with this equation. It relates with the moment of the inertia and the angular velocity. Flywheel, the characteristic of flywheel includes a high energy density. Okay, we have energy density, so it's quite compact. And high short-term efficiency, you can see here, more than 18%, much higher than the compressed air, right? Compressed air only 14%. It has more than 18%. But the scale tends to less than 20 megawatts. And one of the most significant advantage of flywheel is the response time. It can respond very quickly, even in milliseconds. So it's very suitable for use for some UPS situations. Okay. In terms of the development of flywheel technology, it was proposed in the 1950s, but developed slowly due to the limitations of technology and the hardware at the time. So maybe each technology has their moment. Okay. So in the early 1980s, breakthrough in the high temperature superconducting magnetic that makes it more feasible. Okay. Here is another short video.
Illuminessa 親和人體配方，傳承母乳保護。
Okay, now we have discussed all of the technologies that convert electrical energy into the mechanical form, and in the following part we will discuss the technologies that is stored directly in an electrical form, and also the battery. Okay, we may have a like 10-minute break. Okay, like we will come back in the 10:40.